All right, it's just continuing on with this example 4 from the textbook, and I was just looking at what's the probability the next car to pass the lights is red. So as I said, without actually collecting this data, without working out these relative frequencies, I would just be guessing that. Okay, so if I hadn't have stood there and counted how many red cars out of the 500 I counted, really, if I was trying to give you the probability of red, I would just be completely just guessing it. So by doing this work, by getting the relative frequencies, I am able to work out probabilities. And then as I see in the next part, I'm able to then make predictions about the future based on my relative frequency. So part 5, use the information to estimate the frequency of each color if 2,400 cars pass the lights in a full day. Write this information into the table. So I collected data about 500 cars, and now I'm going to make predictions about 2,400 cars. So if 14% of the cars that went by were red, then I would guess that out of the 2,400 cars that are going to pass in a full day, 14% will also be red. So 2,400 multiplied by 14% is 336. I said that 20% or 0.2 of the cars are blue. So of the 2,400 cars multiplied by 20%, I would predict that 480 of those will be blue. Okay, the full way down, and then they should add to 2,400. All right, the kind of calculations are done down here, further down in the example. So that is using relative frequencies to work out probabilities where you wouldn't be able to do it otherwise, and then make predictions about the futures, come up with what are called expected values. So those daily frequencies there are expected values. Okay, so I'm using my relative frequencies to come up with probabilities to come up with these expected values in the future. Part 6 there, just something to cover off, a little bit of statistics here, kind of the data collected by the students is not a random sample of the cars passing throughout the day. Do you think this makes your estimate in part 5 unreliable? So just, I suppose, you're only standing there for the example says, yeah, the example says you're only standing there for a 2-hour period. So I would say you don't quite have a representative sample. So if you want to make a better prediction about the 2,400 cars that pass in a day, you should go for a few different 2-hour periods. Okay, you should stand there in a couple of different days as well. Okay, so just a 2-hour period, you might just freakishly happen to get more blues than normal, or more silvers than normal, or less reds than normal, or something like that. So the bigger the sample, the better. Okay, so if you were to stand there for longer or come back on a few different days at a few different times of the day, you will get a better sample, you will get better relative frequencies, and you will then get better predictions about the future. All right. Over here, then example 5 and 6, you're going to look at together, and they're a little bit of what we're doing already. So Ida wants to see if this spinner is fair. She suspects that the outcome is more likely to be a 6 than the other two. So they look like about 1/3, 1/3, 1/3 to me, but she kind of thinks this is biased in some way. Okay, it's not just landing on each one 1/3 of the time. Describe how she could find the probability of getting a 6 with this spinner. Well, just keep doing it. Okay, so just keep spinning the thing, and let's say I spin it 300 times. I would expect 100 6s, 100 4s, 100 2s. All right, and the further my answers are away from those predictions, the more confident I might be to say it's biased or not, with the little caveat that I was mentioning earlier about wanting to do as many trials or spins as possible. So in example 6, it says she does spin it 300 times, and here's her results. So she got a 2 40 times, she got a 4 92 times, she got a 6 168 times. So we said if she does 300 spins, they should be 100 each if it's fair. So it does look as though the 4 is roughly in line with what we'd expect. If we're expecting 100 of each of them, 92 4s is kind of around about what we'd expect. 42s is a good bit below what we'd expect. And 168 6s is a good bit above what we'd expect. So we would expect 100 of each of those. We're getting, say, 40 and 168 here. Or else when we did the relative frequency, we would expect each relative frequency to be about 0.33. All right. Whereas if I do 40 over 300, it's 0.13333. So it's well below the probability I would expect when I actually do the relative frequency calculation, when I actually spin it. Okay, again, I would expect 0.33 on the sixes, but what do I get? 168 divided by 300, 0.56. So I expect it to be a 6 a third of the time. It's a 6 over half the time, and approaching in on 60% of the time. It's a 6 rather than the 1/3 I expect. So yeah, if I was suspicious it's biased, that wouldn't change my mind. All right. So yeah, it appears that that spinner may be biased. It's not giving fair results. It's not going a third. It's not a third chance of each of them coming up. But again, okay, if you look here, we can say that this spinner appears to be biased in favor of 6. More trials would be needed in order to say this with more confidence. So always put that little sentence in there that you would like to do more trials to figure out for sure if it's biased. So you don't want to spin it 300 times. You want to spin it 3,000 times, 30,000 times, 3 million times. Okay, and if it's still biased after 3 million spins, then you're starting to, yeah, okay, yeah, it seems to be biased to me. So just in an exam, I would always cover off that you want to do more trials to say for sure. All right, that's the end of the examples in your book. I'm just going to jump back and quickly look back at a couple more examples from the first year book, just on the actual nuts and bolts of calculating probabilities, and then I will finish up. So just these ones are all about a deck of cards. So if you're not familiar with a deck of cards, you do need to know it. All right, so just it's there on the bottom of page 105, or just Google it and just kind of make sure you know exactly what makes up a deck of cards in terms of the numbers, the face cards, the suits, etc. All right, and that's what these examples are going to be about. So example 1 here, a card is picked at random from a deck of 52 cards. Find the probability. It is a 6. So there's 4 6s in a deck of cards, okay? 6 of hearts, 6 of diamonds, 6 of clubs, 6 of spades. So there's 4 of them out of 52 possible cards. So you go 4 over 52 and then just simplify it on 1 over 13. Okay, so I would say fractions or decimals for probabilities. Okay, percentages are all right as well, but you will generally see them as fractions or decimals. If you're writing them as fractions like this, just simplify the fraction as much as possible. Part 2, then, the probability of a spade. So P bracket spade is probability of a spade. So there's 13 spades in a deck out of 52 cards, simplifies to 1 in 4. So it's a 1 in 4 chance you'll pick a spade at random. Probability of picking a black card. So you've got spades and you've got clubs. So you've got 2 of the suits are black. So that's 26 cards out of 52 is 1 over 2. Or else you could have said that means 2 suits out of 4, and that also simplifies to 1 and 2. The probability you get the queen of hearts, well, there is only 1 queen of hearts in the pack. So 1 over 52. Part 6, then, the probability of getting a spade or a club, well, there's 13 spades and 13 clubs. Or means you add them together. So 13 plus 13 is 26 over 52. So that's 1 in 2. Okay, just want to be careful of, let's say there was a part 6 here and it said, what's the probability of getting a spade or a jack? Well, there's 13 spades in the deck and there's 4 jacks. So you might be tempted to go 13 plus 4 is 17 and 17 over 52. But one of the spades is the jack of spades. Okay, so you are double counting a card by putting it into the 13 spades and into the 4 jacks. Okay, the fact that it's both doesn't make it twice as likely to be pulled out at random. Okay, so just make sure nothing's double counted when you're doing those or ones. So the probability of a jack or a spade would be 13 plus 4 is 17. Take away 1. So you're taking out of 1 category, you're not double counting it. So 16 over 52, and just simplify that fraction. Okay. A coin is tossed 300 times. How many times would you expect the outcome to be heads? So look, we've seen this before. It's 1 and 2. So 150 heads is what we would expect. Again, if I did it and got 160 heads, I wouldn't be kind of mouthing off and saying this thing is biased. This is an absolute disgrace. You put weights in the coin. All right. So It can be a little bit off 150, even if you tossed it 300 times and got 200 heads. I would be saying it seems to be landing on heads too often, but I would want to do more trials before saying it's biased. Okay, and just the two over here to finish up. A card is picked at random from a pack of 52 playing cards. Find the probability it's not a king. So there is 4 kings in a pack. So 4 over 52, it's a 1 in 13 chance that it is a king. So the probability it's not a king is 1 minus 1 over 13 is 12 over 13. So the probability of it not being a king is 1 take away the probability of it being a king. We saw an example like that at the start. Example 4 we've covered before, so I won't go through that, or we've covered stuff very similar to it before. All right, so that's a review of the probability that you would have done already in first year, going through, as I say, the examples in the higher level book and jumping back and doing a few in the first year book as well.